Hello, this is Dr. Benjamin Norris from the Chemistry Department at Frostburg State University. Today we're going to talk about representing organic structures using condensed structures. The molecule shown on the right is isoamyl acetate. Isoamyl acetate is an ester that is a principal component in the flavor and aroma of bananas. We are used to using Lewis structures to represent molecules, and we learned how to use them in general chemistry. And for relatively simple molecules, like the one I have shown here, a Lewis structure works out pretty well. However, here's the Lewis structure for isoamyl acetate. You can see that it's starting to get pretty busy, and it's getting to be tough to interpret exactly what the structure looks like. Organic chemists throughout the years have recognized this problem and have proposed multiple solutions. One of them is called a condensed structure. Condensed structures were invented not only to help ease interpretation of structural information, but also to provide a way for structures to be easier to typeset in written documents. To show an example of how a structure can be converted into its condensed form, we will start with this one, which is ethylamine. First, we can take the nitrogen with its two hydrogens and replace that group with the letters NH2. We can also take the CH3 at the other end of the chain and condense it down. Note that some folks like to write H3C for groups that are on the left side of a molecule. I prefer CH3, and I will generally write them that way, though you might see some H3Cs creep in because the software program I use prefers the second way. Then we take the carbon with the two hydrogens that's in the middle, and it can be collapsed down into a CH2. So the final condensed structure is CH3, CH2, NH2. Notice how the way we write the condensed structure is similar to the way you would write a chemical formula, but instead of grouping all atoms of the same element together, they are kept in little clusters to try to indicate how they are connected in the structure of the molecule. Let's see some common condensed notation for multiple groups that you might see in an organic compound. We've already seen CH3 and CH2. For a carbon that has only one hydrogen on it, we would represent that as CH. We've seen NH2, but nitrogen can have fewer bonds to hydrogen, so here's NH. The OH group is condensed as OH. The carbon-oxygen double bond is condensed as a C followed by an O. If the carbon-oxygen double bond has a bond to hydrogen on one side of it, it's condensed to CHO to avoid confusion with the OH functional group. If the carbon-oxygen double bond has another oxygen on one side of it, it's condensed to CO2. In the first example we did, we considered a molecule where all of the multivalent atoms are in a single straight chain. However, branches are very common in organic molecules. So let's look at how we condense the structure of a molecule that has a branch in its order of its multivalent atoms. This is the structure of the amino acid valine. First, we can condense some common groups down into their condensed form. Already in this partially condensed structure, the structure of valine is much easier to visualize and interpret. However, we can go farther. The group that I just circled in the structure on the right can be condensed into the condensed form shown below. That carbon has one hydrogen bonded to it and two CH3s, so we can group the two CH3s together in parentheses like perhaps you've done in writing out the formula of a complex ion or an ionic compound with multiple copies of the same ion. So we have two CH3s attached to the same carbon. We group them together in parentheses. Now all we're left with is representing the carbon in the middle of the structure that has a hydrogen, an NH2, a CO2H, and the other carbon group on the left. That group can be represented as CHNH2, but we need to put the NH2 in parentheses. In this case, the parentheses is indicating that NH2 is attached to that carbon atom, but not part of the main chain of the molecule. And here's the final condensed form. Two CH3s attached to a CH, attached to another CH, which has an NH2 coming off of it, attached to a CO2H. Here's another example. Let's go back to isoamyl acetate. First, we can condense down all the CH3 groups, as we have done before. And again, just this simple act already makes the structure much easier to interpret. Now let's condense down this group here using the rules that we've talked about. It's now CH3, CO2, CH2, CH2, and then finally we condense the branched group at the end. The final condensed form is shown at the bottom right: CH3, CO2, CH2, CH2, CH, and then two CH3s attached there. Up next, we'll be talking about representing organic structures using bond-line structures, the other way that we can simplify the structure of an organic compound to make it easier to represent. Thank you for watching.